Have you ever heard about phonons? Imagine a crystal like a diamond or a piece of salt. Atoms in that crystal are arranged in a neat repeating pattern, a bit like balls connected by springs in a three-dimensional grid. But those atoms aren't sitting still, they're constantly jiggling and vibrating, even at very low temperatures. Think about a guitar string. It doesn't just shake randomly, it vibrates in specific patterns to create different musical notes. The same principle applies to atoms in a crystal. They aren't jiggling independently, but engage in coordinated, collective dances, creating intricate vibrational patterns throughout the entire structure. This collective motion doesn't stay put. The energy propagates through the material as a wave, much like ripples spreading across a pond. It's not the matter itself that travels far, but the wave of energy passing through it, transferring momentum from one point to another. And here's the quantum twist. We've established these are waves, but in quantum physics, every wave can also be described as a discrete packet of energy, a particle. For sound waves in a solid, those particles are called phonons. They aren't real physical particles like electrons or protons, but rather quasi-particles, a useful way to describe how energy and vibration move through matter. While you can't see them, the effects of phonons are all around us. These quantized vibrations are crucial in many everyday phenomena, from feeling warmth to powering advanced technologies. Take thermal conductivity. When you touch a hot object, that sensation is transferred by phonons. Heat in a solid is just atoms vibrating, and phonons are the packets of energy that carry this motion through the material, passing it from one atom to the next. They also dramatically influence how electricity flows. As electrons move through a wire, they can be scattered by these lattice vibrations. This scattering is what we experience as electrical resistance, causing devices to heat up. But under special conditions, phonons can actually help electrons pair up, allowing them to glide effortlessly through the material. This is the basis for superconductivity, where electricity flows with zero resistance and zero energy loss. So to recap, phonons are the quantum packets of vibration that ripple through the atomic lattice of solids. Just as photons are the fundamental particles of light, phonons are the fundamental units of sound and heat. They are the discrete, quantized bits of energy that make up the invisible symphony playing out at the atomic scale. Though invisible, their influence is profound. Understanding them explains not just why materials conduct heat or how sound travels, but it also unlocks future technologies. By controlling phonons, scientists can design better insulators, create devices that turn waste heat into electricity, and push the boundaries of superconductivity. They are the unsung heroes of the material world.